Hi, my name is Edgar Casillas. This workshop will talk about magnets, elements, different compounds, and so many cool stuff you didn't know. When I was a little kid, me and my dad always collected scrap metal, and to determine whether if it was iron, copper, or aluminum, we always used a magnet. If the magnet got stuck to the metal, then it was an indication it was iron, and the rest were either copper or aluminum depending on color and weight. This technique always made me think that only iron had an attraction to the magnet, while the other metals never did. On today's workshop, you will get to learn about magnets and how they work, and also determine whether my statement, if it sticks to a magnet, then it's iron, is really true. We first need to understand what a magnet is and how it functions. A magnet is an object made of certain materials which create a magnetic field. Magnets are available in all sorts of shapes, including discs, rings, blocks, rectangles, arcs, rods, and bars. They are made out of materials such as ceramic, alnico, rare earth material, and flexible rubber-like materials. But why are they so important? Not only do the shape and material of magnets vary, so do their applications. At many companies, magnets are used for lifting, holding, separating, retrieving, sensing, and material handling, just as you see in the pictures. You can find magnets in a car and around your house, whether it is to hold papers on a refrigerator or whether it is to wash your clothing. Magnets are used everywhere, and they're really important. But how were magnets discovered? There is a legend that talks and goes back 4,000 years ago in ancient Greece that talks about a shepherd named Magnus. One day while he was taking care of his sheep in an area of northern Greece called Magnesia, he noticed that the nails of his shoe and the metal tip of his stick became firmly stuck to the large black rocks where he was standing. He was actually standing on lodestone, which is a rock really black, as you can see in the picture, that had a magnetic field. This rock can be considered a natural magnet. Ship sailors from Greece thought that Magnesia was a haunted place because every time ships passed through it, they will break and collapse. Magnesia was full of lodestone minerals which attracted the iron, so when the ships passed near this place, the nails from the ship will get attracted to the lodestone, come off, and the whole ship collapse. Later on, people discovered the magic of this stone and how it attracted only iron. This is why magnets are called the way they are, because they were discovered in Magnesia and also due to the fact of who discovered it, which is Magnus. Magnets are objects that have a north and a south pole at opposite ends. A magnet contains electrons that have both uneven orbits and uneven spins. Those magnetic atoms are aligned in a nice straight row inside each domain, and those domains also line up all in the same direction. A magnet itself isn't moving, right? But if we look closer, there are charges inside it that are moving. Inside the metal, the electrons are orbiting the nucleus of each atom, and when charges move, they produce magnetic fields. We will talk a little bit more about what magnetic fields are and on the next slides. In a lot of non-magnetic materials such as wood or silicon, there are electrons orbiting both directions, and their magnetic fields cancel out. But in some special materials such as iron, there is not an even number of electrons orbiting both ways, and overall the magnetic field is produced. That's why you're able to actually connect an iron piece with a magnet, and you will see the attraction in between them. If we take a closer look at what a magnet is, we also see that it actually connects with the north and the south poles of each end. Now, what happens if you connect the north with the north or the south with the south on between each magnet? You will see a repulsion. They will both repel. Even if you try hard, it will still repel. Magnetic fields are areas where objects exhibit a magnetic influence. The fields affect the neighboring objects along things called magnetic field lines. A magnetic object can attract or push away another magnetic object. If you place an object in a magnetic field, it will be affected, and the effect will happen along the field lines. We cannot see these field lines that go around the magnet, but if we put little pieces of iron around the magnet, we can definitely see the lines forming around it. So the first thing that you're going to do, so we could look at magnetic field lines on the magnet, is that you're going to put a piece of paper below the magnet, as you can see on the picture over here. Then what we're going to be doing is you're going to put a piece of plastic topper or container, and then what we're going to do is you're going to get some pieces of iron, and then you're going to splash it around the magnet. This is iron little pieces, and we could actually see those magnetic field lines forming on the iron. They're not necessarily forming, they're actually already there. They're just invisible and we cannot see them. But doing this iron test proves that these magnetic field lines actually exist. And it'll exist on all the magnets. That's what makes the magnet, those magnetic field lines. That's what attracts the iron with the magnet. And that's what pulls them together. Now, one of the things that you will have to know also is that the magnet is actually our Earth. Earth is considered a big, huge magnet. And as you can see in the picture, it also has magnetic field lines. Now, have you ever thought about what those magnetic field lines help the Earth? Well, let's go deeper and see how it actually helps us, how it helps the Earth, and how it helps us survive. Of all the planets that orbit the Sun, we know that only 2 are suitable for life. And those 2 are actually one of the few that contain the magnetic field lines. But which one has a more stronger magnetic field line? Well, it's obviously Earth, right? But let's talk about the Sun, the Earth, and Mars. What's the difference between them? We know that the Sun is the one that gives us power. It gives us energy. Both planets have surfaces warm enough for liquid water to cool on. But while the Earth is blessed with warm liquid oceans, Mars is dry and dead. The Sun is constantly releasing deadly radiation towards Earth, and only the magnetic shield saves us. Without it, the solar wind will blow us apart and will blow out the atmosphere and will dry the whole Earth down, and nothing on Earth will exist. And that's why we should be thankful for those magnetic field lines. Now imagine that you are a person that got lost on the ocean, or that you're just at home and you want to go to a field trip to the mountains, and you suddenly don't even know where you're at. You're in the middle of nowhere. Well, this is why we have a compass. If you've ever seen a compass, you know that it's usually a simple round object that contains a small, lightweight magnet, right? It's like a needle shape that is balanced on a pivot point that allows it to move freely. One end of the needle is often marked with a N for north, since that end, and the other side is also the South Pole, right? How cool is that such a simple magnet object exists that can tell you which direction north is, no matter where you go on Earth? As we learned before, Earth is like a huge magnet that creates its own magnetic field. The north end of the compass is drawn to align with Earth's magnetic North Pole. As explorers have always known, you can orient yourself and travel purposefully in a specific direction as long as you know which way is north. If you need to use a compass to navigate thousands of miles, it's important to know that there is a difference between Earth's magnetic North Pole and true north, which is Earth's geographic location known as the North Pole. Earth's magnetic North Pole is actually about 1,000 miles south of the geographic North Pole. Further complicating navigating by compass is the fact that Earth's magnetic North Pole can move. Earth's magnetic field can change over time. Further complicating navigating by compass is the fact that Earth's magnetic North Pole can move. Earth's magnetic field can change over time. As it does so, the magnetic North Pole moves. Scientists at Oregon State University believe that the magnetic North Pole has moved over 620 miles towards Siberia over the last century, which is actually impressive. Finally, Earth's magnetic field is not uniform all around the world. Changes in altitude and geographic landforms in certain localities can cause disturbances that affect the accuracy of a compass. The difference between the true north and the magnetic north in a specific area is measured by an angle called declination. But despite these issues, compasses are valuable tools that can help you and could guide you to different journeys in your life, whether you get lost or whether you just need some perfect direction. They will help you, and they will actually help you based on the magnetic field lines of Earth. Now I'm going to be talking about my favorite subject, which is chemistry. We talked about the history and the things that make up a magnet. But now I'm going to talk about different elements and compounds that have a magnetic attraction. For instance, copper, which is found in a penny. Do you think it's attracted to a magnet? You can put a magnet and see if it connects, and you will conclude that it's not an element that has magnetic attraction. But let me tell you that this theory is wrong. Copper does have a magnetic attraction, and I will explain why this is the case.
You will also learn of different compounds that actually have that magnetic attraction.
Paramagnetism is the attraction between a magnet and another substance. For example, if you place a piece of metal, iron, into the magnet, that attraction is automatically seen. Automatically, you will see that the magnet connects to the iron. That is the definition of paramagnetism, the attraction between a magnet. Diamagnetism is the opposite of paramagnetism, is the repulsion of a magnet in between another substance. For example, if you put a piece of graphite, you won't see that any attraction. They will actually repel. That is diamagnetism. Or if you put a piece of wood into a magnet, you see that it doesn't have any connection between them, right? That is diamagnetism. Now, the study of chemistry is the study of matter. What will happen if you add this chemical to that other chemical? Or how and why does this compound behave in its natural matter? On the next slide, we will talk about matter and how it is very important in magnetism. Matter is everything we see and touch. Matter is composed of all the living things, and the purest form of matter are elements. The Virtual School Academy will talk about atoms and also what is composed of every atom and element, and how will it be useful to our understanding of magnetism.
When you look at the periodic table, you will see that each element has its own box. And within that box, you'll find two numbers: the atomic number, or proton number, and the mass number. But what do these numbers mean? The atomic number has a symbol Z. This number tells you how many protons are in one atom of an element. The number is always the same for all atoms of a particular element. Atoms of different elements have a different atomic number, meaning they have a different number of protons. For example, an atom of hydrogen has an atomic number of 1 because it has 1 proton. But an atom of oxygen has an atomic number of 8 because it has 8 protons. The next number we look at is the mass number. The mass number has a symbol A. The mass number tells you how many protons and neutrons are in one atom of an element. We need to remember that protons and neutrons each have a relative mass of 1, and that electrons are so small that their mass does not need to be considered in the mass number of an atom. So if we know the mass number of an element, and we know the atomic number, we can calculate the number of neutrons in an atom of a particular element. So the mass number equals the atomic number plus the number of neutrons. The atomic number is just the number of protons in an atom. Therefore, mass number equals protons plus neutrons. So if we take oxygen, oxygen has a mass number of 16 and has 8 protons. But how many neutrons does it have? Remember, mass number equals protons plus neutrons. We can rearrange this to show that neutrons equals mass number minus protons. Neutrons equals 16 minus 8 equals 8. Oxygen therefore has 8 neutrons. Let's take another example. Lithium has a mass number of 7 and has 3 protons. How many neutrons does it have? Mass number equals protons plus neutrons. We can rearrange this to show that neutrons equals mass number minus protons. Neutrons equals 7 minus 3 equals 4. Lithium therefore has 4 neutrons. So the atomic number is the number of protons in an atom, and the mass number is the number of protons and neutrons in an atom.
Atoms are really small, but we can get smaller. If we zoom into an atom, we find that it is made up of protons, neutrons, and electrons, and a lot of empty space. Imagine an Olympic swimming pool, 50 meters wide. This is our atom. At the center of our atom is the nucleus. The nucleus is made up of protons and neutrons. But if we jumped into the pool to find the nucleus, it would be pretty much impossible, because it is the size of a grain of sand. Around the nucleus, we find that electrons are randomly whizzing around. The electrons are even smaller than protons and neutrons. So say we only have 2 electrons in our atom. These would be randomly moving around our grain of sand in our 50-meter pool, just these 2 tiny electrons. So what does that leave? A lot of empty space. Now if we think about the minuscule scale that we're talking about, the constituents of an atom must have a minuscule scale to match. If we were to weigh protons, we would need 600 sextillion to just weigh 1 gram. So one proton would have a very, very small mass, and the same is true for neutrons and electrons. This is why we weigh them in relation to each other. We assign the mass of a proton as 1. The neutron has a similar mass to protons and is also given the mass of 1. The electron, however, is much lighter and has a mass of 1/1840. If we think about how heavy the mass of the protons and neutrons are in relation to the electrons, it's clear to see that the mass of an atom is concentrated at the nucleus. Protons, neutrons, and electrons also have a charge associated with them. Protons are positive, neutrons are neutral, and electrons are negative. The charge of an atom is always neutral. This means there must be the same amount of protons as there are electrons in an atom. The number of neutrons can vary, and they do not affect the charge of the entire atom.
Get ready for a problem practice set. On this problem, I want you to tell me how many protons, neutrons, and electrons there are in aluminum and copper. Please pause the video until you complete and finish the practice problem and understand the answers. Let's take a look at what your answers are. Aluminum has 13 protons and 13 electrons. Now remember that the atomic number is always equal to the protons and also electrons if the element is uncharged. And the number of neutrons is equal to mass number minus the number of protons. So in the case of aluminum, 27 minus 13 protons will be equal to 14 neutrons. Now copper. Copper has 29 protons, 29 electrons because it's uncharged, and also 35 neutrons. I'm rounding the mass number to 64, so 64 minus 29 will equal 35 neutrons. If it doesn't match your answers, please go back again and solve the problem once again. Remember that this will be on the quiz in order for you to pass this workshop. The periodic table is a tabular arrangement of the chemical elements by increasing atomic number, which displays the elements so that one may see trends in their properties. This table was organized and created by the Russian scientist Dmitry Mendeleev in the year 1969. On the next slide, Dr. Cal will talk about electron configurations of every element in the periodic table and how to write and predict the electron configuration for every element in the periodic table.
The first thing we need to do to find electron configurations is to find the number of electrons for the element. So we can find this on the periodic table, and we're going to look at the number above the element symbol, which is called the atomic number. That'll tell us the number of protons, but it also tells us the number of electrons. And we can use that number as we try to find the electron configuration for whatever element we're interested in. So we'll move helium over to group 2 since it fits better there for electron configurations. We have our periodic table, and we just need to memorize that every element in group 1 ends in S1, group 2 ends in S2. We'll go over to the P block. Those elements in group 3, they end in the P1, and then P2 all the way up to P6. Going back to the transition metals, we start with D1 and go all the way to D10. For boron, we'll look first at row or period 1 on the periodic table. We can see that the hydrogen has atomic number 1. It is in row 1, so we're going to write 1 down. That's the period. It's also the energy level for the orbital that we're talking about. Then we'll go to number 2, which ends in S2. So we're going to call the first part 1s2, and then we're done with period 1. We'll go to period 2, and we see that lithium, atomic number 3, that ends in S1. Next, beryllium, that ends in S2, and those are all of the S's in that second period, or energy level. So we're going to put 2s, and since there are 2 electrons there, 2. Now we're going over to the P block, and we're at boron, which is the element we're writing the configuration for, and we can see that boron ends in P1. Now we're still in the second period, so it's going to be a 2p, and boron ends in 1. So that's it. That's the electron configuration for boron. We'll do chlorine the same way we did boron. In row or period 1, we can see with hydrogen, we'll start atomic number 1, we have the 1s1 and 1s2 full, so we just write 1s2. We go across, and we're actually back in row or period 2, so we have lithium and beryllium, 2s2, that's full. We go over to the P block, and we have all of that full, P1 through P6, so we just need to write 2P6. We go down to row 3, we have 3s1 and 3s2, those are full, so we write 3s2. We're back over across to the P block, and we can see chlorine's there at P5, so we're almost there. So we put 3P, and since chlorine's in the P5 group, 3P5. That's the electron configuration for chlorine. We'll try one more, vanadium. So vanadium has atomic number 23, so we have 23 electrons, and we're going to go through the periodic table until we get to vanadium. So we'll start in period 1, there with hydrogen, atomic number 1, and we see the 1s1 and 1s2, those are full, so we'll write 1s2. Now we move down to the second period, we have the 2s1 and 2s2, those are full. Then we go across, we're into the 2p's, and all of the p's are full, so we'll put 2p6, down to period 3, 3s2, then we have all of the 3p's, those are full as well, so 3p6. We're down to period 4, and we're getting close to those 23 electrons that we have for vanadium. So in period 4, we have 4s1 and 4s2. Those are full, so we'll write 4s2. And then we're into that D block there, and if we go over 1, 2, 3, that's where vanadium is, so we would expect that we would have 4d3. However, this is the one exception that you need to be aware of if you're using this method. When we get to the D block, we always take one away from the period number. So instead of 4d3, we would have 3d3 as the electron configuration for vanadium. So at this point, it really becomes just a matter of practicing them. Do them yourself, struggle with them, and then look at the answer. And go back and do this until you can get them right every time. The pattern's pretty much the same for all the elements. You just continually add electrons on.
The spin of electrons creates a magnetic field on every electron configuration. If the electrons are unpaired, then those electrons create a magnetic field, which will be paramagnetic. Now, if the electrons are all paired in the electron configuration, then they will be diamagnetic. As you can see here, the unpaired electrons on the boxes are what makes this element paramagnetic, while the paired electrons on the boxes below make it diamagnetic. Now take a look and pause the video and tell me whether each of the 4 elemental ions will be paramagnetic or diamagnetic. Now let's look at the answers. If you answer diamagnetic for calcium 2+ and zinc 2+, which are further up, you are correct. Both of the electrons are paired, which will make them diamagnetic. Now let's take a look at the 2 elements below, which are copper 2+ and manganese 2+. Both of these ions have unpaired electrons, so that means that they are both paramagnetic. On the next video, we will talk about paramagnetic transition metal ions, which are the ones that are listed in this page. Jeff Braken will talk about the relationship and how both of these are classified as diamagnetic and paramagnetic.
Oftentimes when we go through quantum mechanics, we're stuck talking about things that the students cannot see. They have to almost take our word for it that we're telling them the truth. Whether it's flame tests or orbitals and where the electrons are, There's an awful lot of abstract things going on as we talk about quantum mechanics. What we have here is a nice way of showing, connecting some of the theory with reality. What I have here would be small pipettes. If I hold it this way, you might see a little bit better. Small pipettes with solid material in each end. And they're stuck on these little black elbows so that they form a large V. You see that I have a calcium salt in here, a zinc salt here, a copper salt down at the lower left, and then a manganese salt on the lower right. Well, there are some interesting properties that these will show when subjected to a super strong neodymium type of magnet. But in order to understand what we hope to see, we want to take a closer look at the electron structure. So what we see in the calcium ion example, what we see would be the 3p6 electron picture, where we have 6 electrons in the 3p series of orbitals. The big idea here, students would recognize, we have no unpaired electrons. Everything's partnered up. There are 2 electrons in each circle or each orbital. Over here, we see the zinc ion example. The zinc plus 2 ion has a full 3d10, as we would call it, because it has 2 electrons in each of the 5 d orbitals. Again, no unpaired electrons. Down here, we see, in the case of the copper plus 2 ion, we see a 3d9 electron configuration. And again, we would see 2 electrons, 2 electrons, 2 electrons, 2 electrons, and 1 unpaired electron. Again, students are comfortable with that, but why is it the way it is? We'll talk about that. Here, the manganese plus 2 ion has a total of 5 electrons in its outermost electron orbitals, and we see a 3d5 electron configuration. And we spend a lot of time talking about how electrons, being negatively charged, naturally repel each other. They try to get as far away as possible. That is, if we make the electrons come to life and have feelings. But we see 1 electron in each of the respective orbitals. That means we have 5 unpaired electrons. So we have, some of these have no unpaired electrons. The copper has 1 unpaired electron, and the manganese has 5 unpaired electrons. What I also like about this is the fact that here we don't have any d orbitals present, or they're unfilled. Here I do have a d orbital, or d orbitals, d orbitals, and d orbitals. But now let's go over and subject each of these to a very strong magnetic field. This is a super strong neodymium type of magnet, very, very strong. It has to be the super strong neodymium magnet for this demonstration to work. And what I'm going to do with the calcium ion, and its no unpaired electrons, see what happens when I take this super strong magnet next to it. There's no effect. Now let me go to the zinc plus 2 ion and see if we can get that to be subjected and move. Not moving, unaffected by a magnet. So in the first 2 examples, what we've seen, with no unpaired electrons in the calcium ion or the zinc ion, no unpaired electrons, unaffected by a super strong magnet. Now we're going to go to the lower level, the copper plus 2 and the manganese plus 2, and see what the effect is when we subject those to a super strong magnetic field. starting with the copper ion with its one unpaired electron. We're able to see some slight deflection here. So there we go. Just a little, there we go. Definitely is moving, but not very strong. And that's with one unpaired electron. Now, with manganese, with its +2 charge, it has 5 unpaired electrons. Well, if no unpaired electrons are unaffected by the magnet, one unpaired electron is slightly affected by a magnet, now we're going to be able to hopefully see what happens when manganese is subjected to a strong magnetic field. This would be a time as a teacher where I'd say, make some predictions. Why do you think that? And you can see I can pull this literally all the way around, twisting the rope up on top. Very, very affected. So the terminology that we use here, no unpaired electrons, the science word for that would be diamagnetic. Okay? No unpaired electrons. Down here, these two examples are what we call paramagnetic. They have unpaired electrons in their respective orbitals. And with so many unpaired electrons in the manganese, it's no doubt or no question as to why or how, if we have to explain, why is this one so easily moved by a magnet, whereas the copper is only weakly attracted. Okay? Again, it's easy in the quantum mechanical world, in our quantum unit, to become bogged down and really leave it at the abstract level of an orbital chart, but it's a nice example here of connecting the atomic world and where the electrons are with a macroscopic property such as being magnetic.
If you take a look at copper and connect it to a magnet, you will see that both of them will not connect. We could easily conclude that copper is diamagnetic. However, if we look at the electron configuration of copper, we can see that it has an unpaired electron, which we know that it is paramagnetic. The only form of copper that will be diamagnetic will be copper +1, which shows all of its electrons paired. So next time you think that copper and the magnet do not connect, you are wrong. It actually does have an attraction, but it's really weak. The Lewis structure approach provides an extremely simple method for determining the electronic structure of many molecules. It is a bit simplistic, and does have trouble predicting structures for a few molecules. Nevertheless, it gives a reasonable structure for many molecules, and the simplicity to use makes it a very useful tool for chemists. A more general but slightly more complicated approach is the molecular orbital theory. This theory builds on the electron wave functions of quantum mechanics to describe chemical bonding. The Lewis structure does tell us how different compounds will be attached, but it will not tell us if they are paramagnetic or diamagnetic as the molecular orbital theory does. If we take a look at the liquid oxygen and liquid nitrogen Lewis dot structures, which one do you predict will be diamagnetic or paramagnetic? Let's take a look at the molecular orbital theory of oxygen. Here we can see that the liquid oxygen has some paired electrons in the middle, which will be classified as paramagnetic. So liquid oxygen will have a magnetic attraction. The molecular orbital theory for liquid nitrogen has all of its electrons paired in the middle, which can be classified as diamagnetic. So liquid nitrogen will have a magnetic attraction.
I pour the liquid nitrogen past the magnet's poles. It doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
So, just when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
We have learned in this workshop that iron is not the only element that connects to a magnet. There are an infinite number of elements and compounds that connect to a magnet. So next time you hear me say, if it sticks to a magnet, then it's iron, you know I'm wrong. Thanks for watching my workshop and hope you understand and learned about magnets.